Okay, so today we are doing the layout for the inverter, okay? Layout for the inverter. So the inverter does nothing but inverts the digital signal, right? You can see one thing you need to know, okay? The ratio here is not a ratio for either the PMOS or NMOS. It's a ratio of the width of the PMOS to the NMOS. Keep in mind. It's trying to show that which one is stronger, right? So the wider PMOS or wider NMOS. So look at the ratio, right? Here. 20 means 20 lambda for the PMOS and 10 lambda for the NMOS. Because we consider that the length for the PMOS and NMOS are the same, which is 2 lambda, minimum, right? Minimum length. That's one thing you need to know. Another thing is for the layout, okay, now we are getting CMOS circuits instead of just the transistors. So, which means we have both wells being put into the same layout view. So in that case, make sure that there's no overlap between the N well and the P well. There should be a gap. Okay, there should be a gap in between. Don't overlap them. And for the N type and P type, as what we did before, make sure there is an overlap. Because N type is typing N well and the PMOS is in the N well, right? Similar to the NMOS. Okay, and the next example, the very last example shows you that a bigger transistor will give you a stronger driving capability. As the way to do that is there's a parameter called M, multiplier or something, and you can put a number over there, so it's going to be 5 times the width. So it's going to make this transistor stronger in general, okay? It's going to make it stronger. So M is 5, so 5 means, here, 5 means 5 times the width. Keep in mind. We are just making it wider but not longer. Making longer doesn't make sense. Making wider, we keep the minimum length for all the transistors and we modify the width. Okay? So 5 times the width will make it 5 times stronger according to the square law equation. Remember, square law equation has a width over length, right? So you have 5 times the width, you are getting 5 times of the current going through the channel. You add a 5 for the schematic, okay? You add a 5 to the schematic. But the thing is, you are not adding like 5 parallel transistors next to it. However, in the layout, because you times 5 already for the schematic, you have to do a wider, 5 times wider of the PMOS and NMOS in your layout in order to pass LVS. So if you look at this inverter, looking at the structure, it looks like a NAND gate, but actually it's an inverter. It's a wider inverter. Why do I know that? Because you can see the gates are all shorted or all interconnected. It's just one gate. So one gate means just one transistor. Okay? Just the one gate, because all the gates are interconnected. So it's just one transistor. And it is shorting these drain connectors. So eventually these ones are in parallel. If you think about the stick diagram, right? How do you make 5 PMOSes in parallel? How do you make the 5 in parallel? Okay, you have 3 wires on the top and 3 wires over here, and eventually they become a parallel PMOS transistor, 5 of them. Same for the NMOSes, okay? Same for the NMOSes. So keep in mind, you have to do a times 5 in the schematic in order to pass NCC, which is LVS. Okay, so for the regular inverter, which is 20/10, So it's a 20 for the width for the PMOS and 10 for the width of the NMOS. Disconnected. For this figure, it's a 20 for the width of the PMOS and 10 for the width of the NMOS. And you can see if I put a 105 microfarads capacitor to light a drive, so drive means it's dumping charges to the cap during the one cycle and pumping charges out from the capacitor during another cycle. It's basically charging and discharging the cap. And I'm trying to use this one to simulate any digital circuits down the road to simulate all these parasitic capacitors. But if I'm putting a 100 femtofarads capacitor over here, this PMOS and NMOS combined is able to drive it confidently, no problem. You can see the edges are not getting significant delay. Even though there is some delay, but I didn't zoom in. If I zoom in, you'll be able to see there's a small time delay. Okay, but the thing is, it's able to totally, you can charge up to VDD and also discharge down to ground. So which means this combination of the CMOS, PMOS, and NMOS is able to drive it. So it's able to drive this 100 femtofarads capacitor, no problem. So if I increase the load, the capacitive load to 1 picofarads, and eventually you can see it's struggling a little bit. Okay, not as smooth as the previous one. It's definitely having some hard time over here. Okay, but still working because it's able to drive it up to 5 volts and discharge it to 0 volts, no problem. But more significant time delay is being observed. If I change it to 10 picofarads, it's totally got disabled. It's oscillating. Okay, so it's unstable. So this wouldn't work. And in that case, you have to slow down your circuit in order to have your inverter to be able to drive this capacitive load. Have to slow it down. So which means you have to extend the duration for the on and off time for the digital signal. If you keep this high speed, you won't be able to drive it, discharge and charge it. So, but if we switch it to the wider one, right? So the wider one is 5 times the width for the PMOS and NMOS. For 100 femtofarads, doing fine, the same as the previous one. 1 picofarads, doing fine, but better, right, than the previous one. And for the last one, it is still able to drive it, even though there's a significant time delay. You can see it, but it's way better than the previous one. So which means if you have a wider PMOS and wider NMOS combined, you will be able to drive a larger capacitive load according to the square law equation, right? So it's having more current running through the 2 channels. So which means when it's charging up the cap, it's dumping more current to the cap, and when it's discharging the cap, it's also able to pump out more charges during a certain period of time. So it's having stronger PMOS and stronger NMOS for both sides. So this serves as a foundation for the larger scale of layouts for the future labs. But I think this is relatively easier compared to others. So if you have any questions, you can ask me. I'll be here. You can get started to work on that.